Great. So thank you all for coming. You're all very small on my screen, so hopefully you'll shout out if you have questions. But I just want to thank the organizers for enabling me to join via Zoom. I really wish I was there amongst you, but didn't work out this time. Hopefully it will next time. So I'm going to focus on using cosmology to probe dark matter physics. And I want to highlight a few of the most recent pieces of work that I'm particularly excited about and tell you about some progress that we've made in that field. And when I say we, I really mean these junior folks who are working in my group at USC, just highlighting the students in the top row, and two amazing postdocs, Ruyan and Ethan Nadler, who's doing a joint position between USC and Carnegie. And then also a whole long list of collaborators who enabled also a lot of this work. So just to give you a theoretical orientation of this talk, it's basically this. We've looked for the WIMP for a while. We haven't seen it. And now what we're left with is this. So hopefully a lot of people recognize this as a famous Tim Tate slide from 10 years ago, summarizing all the beyond CDM paradigms that people thought about at that time. And so I want to touch on quite a few of these. But as I do so, I just want to give you a fair warning. I'm not going to take a role of, arguing for one or the other, talking about one candidate being better than the other, but I really want to take a deep dive into cosmological phenomenology of as many of them as I can cover in the time that I have. And of course, the observational context here is that it's an exciting time to be a cosmologist. There's a lot of data coming our way from a lot of surveys. Galaxy surveys, but then also the CMB surveys of the next generation with the high resolution polarization and temperature measurements, the line intensity mapping, and so forth. And the unifying theme for all of these cosmological observables is that there's one big missing piece. We want to understand dark matter mass and interaction. So we want to fill in this question mark diagram. I wanted to tell you, what I think are some of the very exciting progress that we've made in that direction in recent couple of years. So I have a very ambitious plan here with 4 different topics, but a realistic plan would be that I'll get to the first 2 listed on the top. So I want to tell you what we've been learning from near field cosmology from the local universe. In context of dark matter baryon scattering and sterile neutrino dark matter. And if I have time, I'll tell you why you should pay attention to some more work on 21 centimeter global signal in context of millicharged dark matter, and touch on the SA tension, which I think is a particularly interesting topic these days. All right, so starting off with the local universe, looking at the galaxies in our galactic neighborhood. The background story is this, which is basically that almost whatever dark matter microphysics model you think of that affects cosmology, be it fuzzy dark matter, warm dark matter that scatters with baryons, and so forth, all of these different theories alter the way that matter is distributed in our universe, as quantified by the linear matter power spectrum that I'm showing here. And so these different lines, different colored lines, show the matter power spectrum under different dark matter theories. And all the data is bunched up mostly on the left, which is to say that we measure very well the very largest scales, but the small scales, progressively smaller and smaller scales, are yet to be probed in detail. But the good news is that a lot of the surveys that I was mentioning previously are targeting them exactly. And this is where a lot of the differences between cold dark matter paradigm and the non-cold dark matter, so all of these extensions, really show up most prominently. So I want to focus on one specific set of models first, and that's the case where dark matter and baryons exchange heat and momentum through elastic scattering. So this would be the same physics that direct attraction is searching for. But in context of cosmology, I want to focus on sub-GeV dark matter. So dark matter masses that are really not explored in direct detection yet. And so here, what I'm going to do is I'm going to fill in this question mark diagram with scattering between dark matter and, let's say, protons. And so if you want to describe this scattering process for cosmological purposes, you may as well work in context of the effective non-relativistic effective theory of dark matter baryon scattering. And if you do so, you can really easily parameterize a whole swath of models that you can write down by basically defining a momentum transfer cross-section that's shown on the right here as a power law of the relative particle velocity v, where this power law index n depends on the momentum and velocity dependence of the operator that describes this interaction. Okay, so n equals 0 would be velocity independent, spin independent scattering that we know and love in context of direct attraction. And then the unknown parameter of the theory, in addition to dark matter mass, would be the sigma naught, the overall amplitude of this cross-section. And so in context of this particular model, the matter power spectrum, the linear matter power spectrum, normalized to the CDM power spectrum, which is what I'm showing in the plot there, features a cutoff. And this cutoff moves to smaller and smaller scales, so to the right of this plot, as you decrease the cross-section. So when you have dark matter baryon heat and momentum transfer sometime in the early universe, you end up suppressing power on small scales. And this happens because of collisional damping of dark matter structure early on. Because of their interactions with hot baryons that are coupled to radiation, you end up smoothing out the universe progressively more on smaller scales, where the location of this cutoff corresponds to the last mode that entered the horizon before this interaction freezes out. So a cutoff in the power spectrum just means that those seeds of small scale structure that would turn out to be halos in which some of the small galaxies we see around us today live are not there anymore. And so just like in the warm dark matter case, what you should see in cosmologies with dark matter baryon scattering is a lack of structure on small scale, so perhaps a lack of satellite galaxies around the Milky Way. So Ethan led a study, so we together did like kind of an analytic, squiggle approximation of where the bound on the interaction strength should be, that's allowed by the fact that DS and SDSS and Pan-STARRS have seen all the satellites that they've seen. At that time, this was something like 34, 35, above masses of 10 to the 8 solar mass. So above this mass, we saw no evidence of missing satellites. And so from that information, we tried to figure out at what position should you put the cutoff and what interaction strength does that imply. And then also Ethan did the full, probabilistic modeling of the satellite population in the Milky Way, including the galaxy halo connection, including the disruption of subhalos by the Milky Way disk, marginalizing overall the parameters of this model, and then also marginalizing over the uncertainties on the Milky Way halo mass and so forth, and doing all this fancy analysis produced the line that you see is the red exclusion curve here. So two interesting things at that point were that this was the first astronomical bound that touched on the tip of the direct detection exclusion region. So we're starting to meet these different, very different approaches to the same physics. It extended down to, the limit on the warm dark matter mass. So it went down, far down in sub-GeV regime. And then also we were able to push the bounds by several orders of magnitude with respect to what we had prior to this analysis from the CMB and Lyman alpha forest. So small-scale structure is a particularly powerful probe to test the dark matter microphysics, in this case, shown on the case of velocity-independent, spin-independent dark matter baryon scattering. And you can, of course, complicate this scenario and ask the question, okay, what if I have perhaps more interesting physics? I write down more complicated operators and I end up with a velocity-dependent interaction cross-section. And in this case, a really interesting cosmological phenomenology arises. So in the case where there is velocity dependence, increasingly stronger velocity dependence, you end up with transfer functions or linear matter power spectrum that features dark acoustic oscillations. So you can couple dark matter with baryons so strongly that you initiate acoustic oscillations in dark matter fluid itself, and that imprints a particular scale that's shown in this plot here. So here I'm showing 4 different velocity dependencies. But the challenge with looking at models that have these dark acoustic features is that they no longer correspond to simulations that we have and love that include warm dark matter and a simple smooth cutoff, where we were able to match the interacting dark matter models to warm dark matter and just simply use the bounds on warm dark matter like we did in this study. We no longer can do that because now we have this funky transfer functions with large dark acoustic oscillations. So back in the day, this was a few years ago, we decided to instead just use the bound on warm dark matter that was available at the time. So this is the black solid line, again, obtained from DES and PanSTARRS bounds. And then ask a question, okay, for these dark acoustic oscillation models, velocity-dependent scattering, what are the interaction strengths where we ensure to have stronger suppression of power than in the most suppressed warm dark matter model that's still consistent with the data? Okay, so we're, in other words, looking to pack all these acoustic oscillations generously under that black curve, and then we will call all the interaction cross-sections that correspond to these curves shown in this plot inconsistent with the data. So we're not even going to bother matching, that first cutoff scale to the warm dark matter scale. We're simply very generously going to say we're not going to try to exclude something that has all of a sudden like lots of structure on progressively smaller scales. We're just simply going to say these guys are all inconsistent with the data from what we know right now. And so this was a study led by an amazing undergrad at the time, Karim Amari, who works now as a graduate student with ICTS. And so Karim was able to push the bounds that we had from CMB using this envelope method. Envelope because warm dark matter bound, the black curve here, envelops the excluded models for interacting dark matter. So using the envelope method, he was able to push the bounds on basically all interacting models, looking through different effective theories by orders of magnitude compared to what we were able to look at with the CMB. And, I'm showing here in blue the bounds that Karim got for different models. So each panel is a different model. N equals 0 on the top left is velocity independent bound. And the gray curves is what we had prior to this analysis. So this is something like 3 to 5 orders of magnitude improvement over linear cosmology. So now these are just numbers, so just to give you a taste. This probing, dark matter in this way really is mapping what dark matter interactions are doing about a month after the Big Bang. So this is when the modes that we're observing today are entering the horizon. The next step that we're taking now is actually running the M-body simulations, where we take these transfer functions that you see on the left, along with those dark acoustic oscillations, as outputs from the class code from Boltzmann solvers for that specific cosmology with that specific interaction type. And then we pass them to n-body code and look at how structure forms in a universe with these modified initial conditions. So most of these models that have positive powers of velocity dependence have most of their effect in the early universe and increasingly less as the universe cools down and velocities of particles drop. So in this figure, I'm showing, and this is a slide by Ethan Nadler. So I'm showing in the top the zoom in on a Milky Way like halo along with the LMC that corresponds to the transfer function that's solid in the left plot. And this is what you would get if instead of using the envelope method that I talked about, you actually match the point where the power drops to a quarter of what you had in CDM. So this would be matching for those of you who work on this stuff. This would be half mode matching between interacting dark matter and warm dark matter at the current bound. Whereas the dashed lines on the left represent the curves where the interaction is put at the current upper limit from the work that I just showed you. So this is from the envelope method. And that corresponds to the bottom Milky Way like halo simulation. So what you should take from this is at the limit of the current exclusions that we have from the analysis that I showed you, the analytic analysis that Karim and Mari did, we have very little structure. And those models are actually probably already severely excluded by the data that we have. So the hope is that we can then translate these simulations into halo abundance that's shown on the right. This halo abundance will see a suppression at the low mass end, and that will lead to a suppression of the luminosity function in the Milky Way satellite galaxies. And the hope is that we can push the bounds on these models further using these n-body simulations. And this is just a fun visual that flips between the simulation that has the interaction strength at the dashed line over on the left and one that has the interaction strength at the solid line. So dashed line would be at the current limit. So the one where you see less structure, so not this one, and hopefully there's no lag, but this one, that's where we are with the current analytic bounds. And this is roughly where we hope to be when we do reanalysis of the simulations. All right, and so here, not with results yet. So I'm just drawing. So I'm just waking you up by showing this this figure illustration only. But another project that we're working on right now is actually putting in dark matter baryon scattering into hydrocodes. So running hydro simulations where we actually can turn on scattering between dark matter and baryons. And then the hope is that we can answer questions like, does the internal structure of halos like the Milky Way change in presence of dark matter interactions, dark matter baryon interactions? Okay, so I will move on to the second part of my talk, assuming that the questions are going to be left for later, but if there are any urgent questions, feel free to interrupt me. So far I've talked about how we use near field cosmology to put bounds on dark matter baryon scattering. Yes.
Sorry to stop you. So I think there are two questions.
There are two questions.
Yeah. So
okay.
I have the question about that dark acoustic oscillations. Isn't it that when you run n-body simulation, those oscillations effect gets erased out because, or you will keep them as you evolve in nonlinear evolution?
Yes, we definitely keep the oscillations. What was your concern? Sorry, I didn't hear the first part of your question.
Do you still be able to distinguish those oscillations versus, because many model has the same cutoff length, but maybe the oscillations are not there, like warm dark matter. In n-body simulation, does this oscillation stays, or they get
No.
erased?
They get washed out, but the mapping is not as clear. So it's not like, sorry, I don't think you guys can see I can't see my cursor. So I'm just going to give up on that and try to, oh, can you see the cursor actually?
Yeah. Yeah.
Yeah. Oh, amazing. Okay. So if you take a look here, so obviously the slope is not exactly the same in the case of this blue line as with warm dark matter. But ignoring that for a moment, here we've done the half mode matching. So this is basically matching the position of the first cutoff, right? And yet the suppression is stronger in that case than in the case where you have the suppression will be different, and I'm not showing it here, than what you have in the case of warm dark matter. So the mapping in the case between warm dark matter and interacting dark matter is not as trivial as matching the position of the first cutoff, because you can have a lot of power in those acoustic peaks. So this is the halo mass function in the case of these dark acoustic oscillations. The oscillations are erased, but the amount of suppression is not well predicted by just the position of the cutoff.
Okay.
Does that make sense?
Yeah. Yeah.
Yes.
Yeah.
Okay.
So there is a second.
Hi, I'm not sure if this is a trivial question or not, but when you showed the parameter space that was excluded of the cross sections between dark matter and baryonic interactions, that CMB part, I was thinking that if you have some sort of like the oscillatory structure that you showed before, doesn't that show up in like the BAO data? And is that like, is it not, is the CMB sort of the resolution that we have not powerful enough to sort of to like show up in that data, and like aren't we able to take
that's a good question. So let's see if I can see it here. So but the bottom line is that if you think of it in terms of the linear matter power spectrum that underlies the CMB and so forth, and all the other observables, in the BAO data, you're looking at the position of the baryonic acoustic oscillations pretty directly, right? And in this case, you're talking about a very small imprint at smaller scales in the dark matter distribution, right? So the way to think about it is that the CMB probes scales that are maybe around here, okay, and dwarf galaxies with the measurements from DES are maybe at around K of like 30, 40, something like that. So you have a lot more constraining power by just even detecting the beginning of that cutoff. So by just even looking at this, you can already place a much stronger constraints just by virtue of looking at smaller scales in the case of the CM, in the case of the dwarfs.
Okay, got it. Thank you.
Yeah. Another way to think about it is that by looking at smaller scales, you're looking at the physics happening at earlier times. And so these exclusion plots correspond to looking at interactions that were happening like a month or two after Big Bang. Okay. Are there any more?
There is no more question.
Okay. All right. So sterile neutrinos. So these guys slipped under my radar, my cosmological radar, for a long time. And I recently really warmed up to them. And so just to share some of the excitement, I guess there's maybe several ways why one might want to care about sterile neutrinos as a potential candidate for dark matter. And maybe the most popular one that I hear from people is something like, well, we know neutrinos are there, they're part of the standard model, but they're the least explored sector of the standard model. And so they might have interesting physics going on in there. There might be a fourth neutrino or maybe even more. And so it's a very convenient place to pack new physics without introducing something we've never seen in the standard model before. But then also you may want to invoke additional neutrino species if you want to invoke various mechanisms to explain the smallness of the neutrino mass. So there are theoretical reasons why sterile neutrino is perhaps an interesting candidate. And the story started in the 90s when Donaldson and Widrow originally proposed that this could be a dark matter candidate. And the model at that time included a fourth neutrino species that would mix with the active neutrinos or the standard model neutrinos, but would itself have no electroweak charge. And so the only way it communicates with the standard model would be through mixing with active neutrinos. And then the dark matter candidate would be a linear combination of the sterile component and the active component, where nu A are the eigenstates for the weak interaction. And so the idea there was that in the early universe, while the standard model neutrinos are in thermal equilibrium with the rest of the plasma, very early on, you start off with no sterile neutrinos. And then every time a normal neutrino has an interaction with the rest of the plasma, it continues propagating. There's some small probability that eventually it ends up oscillating into a sterile neutrino right after this interaction. And so once it converts to a sterile neutrino, the sterile neutrino no longer talks very easily to the rest of the standard model. So eventually you build up relic abundance of sterile neutrinos, and this process shuts off when the active neutrinos decouple from the rest of the universe at weak coupling. Problem with this original model is that if you want to acquire the full relic abundance that matches dark matter, you have to live on that DW line shown in this mixing angle versus dark matter mass parameter space. And the problem with that is that sterile neutrinos should also decay and produce observable X-rays. And people have looked at X-ray lines or looked for X-ray lines by turning various telescopes, NuSTAR and others, at various objects, including the Bullet Cluster and Andromeda and the Galactic Center. And they've been able to exclude vast regions of this parameter space that's shaded in gray here. And so, unfortunately, the excluded parameter space also includes the Donaldson-Widrow mechanism entirely. And so then people came up with ways to evade this bound. In a very simple model, de Gouveia and Zhang and others came up with this idea to boost the production of sterile neutrinos in the early universe by adding an interaction that active neutrinos experience, and so more frequently resetting the clock to enable more opportunities for the oscillation into sterile neutrino to happen at lower mixing angles. So the idea was, let's see if we can lower this black line to lower mixing angles by adding an interaction that active neutrinos experience through a scalar mediator phi. And so here's a model that has two additional parameters. One is the interaction strength, lambda phi, that's on the vertical axis here. And the other one is the mediator mass, m phi. And if you want to produce the full relic abundance of dark matter, you have to live on the gray line here. And this gray line has three distinct regions where the production occurs in case A on the top right here, through a heavy mediator, where the mediator is heavier than a GeV. And so you have active neutrino scattering, corresponds to the diagram on the far left. Or in the case B and C, you have a decay of a on-shell light mediator phi. And that corresponds to regions B and C in the plot on the right.
Vera, sorry to interrupt you, so you have 5 more minutes.
Okay, yeah, that sounds good. Thank you for the heads up. So if you do this, you open up the parameter space that's viable for producing all of dark matter, provided the appropriate choice of dark matter mass, mediator mass, mixing angle, and interaction strength. And so between these red lines is where you can live in this particular model. And this is how the bounds from X-rays, the blue shaded region here, are evaded. But neutrino interactions, believe it or not, and maybe there are many experimentalists amongst you, have bounds from various collider and laboratory experiments. And this is a summary figure of the neutrino self-interaction bounds as a function of mediator mass from a white paper that talks about neutrino interactions. And the most model independent one that I want to focus on here is this one, the yellow curve on the top, which comes from the Z boson invisible width. And in terms of the cosmology, this non-thermal production of sterile neutrinos, depending on which production channel you go through, which diagram is relevant in the regime that you're looking at, the dark matter phase space distribution is different. So the three different scenarios, A, B, and C, are shown in colored lines here. The original Dodelson withdrawal mechanism is the dotted black, and then there are other options as well. So now the good news is we can take in these phase space distributions and model them using Boltzmann solvers. And then we can ask a question, what is the structure formation in these models? What the linear matter power spectrum looks like? And so different phase space distributions boil down to different free streaming of these sterile neutrinos that actually produce a cutoff that looks like this, much like what we've seen in warm dark matter scenarios. And so now the work led by Ruyan was to combine the collider bounds on the interaction strength together with what we know about the abundance of Milky Way satellites in order to put constraints in this widely open parameter space. So one of the most interesting results that we got, or rather the most interesting result that we got, was that when you do a combined likelihood analysis of these two pieces of information, you end up entirely excluding the scenario where neutrino self-interactions proceed through a heavy mediator. So you cannot produce a sterile neutrino in this model if you want scattering through a mediator that's heavier than a GeV. That's completely ruled out. On the other hand, if you want a light mediator, so the other two scenarios that I discussed, you really dramatically reduce this available parameter space. All right, so instead of going through the rest as anticipated, I just want to give some food for thought in case there are any Sarah's folks amongst you. I want to get your attention to this work that was led by my student, Trey Driscoll, which basically took into account the fact that, the backstory is that edges saw a signal that's anomalously deep in neutral hydrogen emission from redshift that corresponds to redshift of 20 or so. And all the theoretical modeling that folks have done at that time boiled down to this black curve that you see here, took into account the fact that in novel dark matter theories, like dark matter that is Miller charged, you would exchange heat between dark matter and baryons and cool baryons anomalously, therefore produce this deep signal. But the one thing that nobody has modeled to our knowledge before is the fact that you cannot have heat exchange without having momentum exchange. So all of this power suppression that I was talking about in these dark matter baryon scattering models, they also occur in context of Milli charge. And if you want to model the edge of signal, you have to take them into account. And if you do so self-consistently, the signal shifts to much lower redshifts. And so you end up from black to blue curve. If you want to know more details, check out Trey's paper, and we can share the code as well. But the bottom line is that you cannot produce the edges, something like the edges signal, under a Milli charged model at all. So this is a statement regardless of where the other bounds lie. But also if you want to constrain a Coulomb-like scattering where you scatter with neutral particles, you get very tight constraint on what part of the parameter space is available. All right, I will stop there and I will leave the key points here and take any questions that you may have. Thank you.
So we thank Vera again for such a nice talk at such a late hour. So let's begin our question and answer session. So first.
Yeah, hi.
Hi.
Myself, Vasudev. So I had a question about the neutrino vertices that you showed for the Feynman diagrams. If you can go to that slide.
Let's see if I can answer them. Yeah.
Yes. So like, what are the vertex factor for these interaction vertices?
Okay, so since you're gonna ask me detailed modeling question when I'm anticipating,
No,
I'm gonna point.
So any reference can do, like just
Yeah. Sorry, but what do you mean? What are the vertex factors?
so for any like vertex that we have.
Yeah, so the this is neutrino self-interaction of this format, and the coupling constant is what controls the strength of the interaction. So that's lambda phi, and that's a free parameter of the theory.
Okay.
So we don't know what lambda phi is, but if you want to have all of dark matter be this particular type of sterile neutrino, you have to choose the right lambda phi, m phi, mass of the dark matter, and the mixing angle. So there are 4 parameters you have to choose in a way that produce the right relic abundance. And then you can.
So it's a free parameter.
It's a free parameter. That's correct. So that constraint eliminates one of the 4 parameters, and now you have 3 to constrain with your data.
Okay, thank you.
Yep, you're welcome. And if you want to know more details, this is the paper to look at. Yeah.
Whereas same slide, between scenarios A, B, and C, are you holding the mass constant, the mass of the sterile neutrino?
For this plot, you mean, or in principle?
Yes,
for
this
the
plot.
analysis?
Yeah, this plot.
I don't remember what Rui used for this particular plot. This was meant as an illustration. So I'm gonna guess that the mass is the same, but the production mechanism is different. But then she needed to choose the other parameters as well. So it's not obvious if you're getting at like which one is more constrained and which one is less constrained than why. It's not easy to look at just so this is maybe the most contentful plot to look at. So this is the phase space distribution. In the case, in case A, it's not at all, it's not monotonic, right? In case A, you have this intermediate case, but then in the light cases, they span the heavy mediator case. So it's not intuitive in any way. But the thing that drives the height of the bound, that's the collider bounds. Sure. So the collider bounds are stronger in this case than in the other 2.
Okay. One quick question for the simulations that you're doing with the sort of acoustic oscillations in them.
Yeah.
Would you be concerned about seeing numerical artifacts?
You mean the fragmentation?
Yes.
Yeah. So Ethan's been agonizing over this for the past, I don't know how long. And we've managed to convince ourselves, agonizing in a good way, like as in quadruple checking and making sure that that fragmentation is not an issue for us, because it is in principle for models with a cutoff. And so he's been looking at the initial, tracing the halos back to the initial conditions and looking at the sphericity and things like that. And it looks like the contamination is really, really low. So it looks like we're, well resolved in the regime that we care about.
Hello. Hi, Vera.
Hi.
Same slide, different question. In these dark acoustic oscillation simulations, are you modeling the dark matter baryon interaction in the n-body simulation? In the n-body simulation itself, or just in the initial conditions?
Just in the initial conditions. And hi, I now know who you are. Sorry, the camera did not move. Yeah. So just in the initial, so these are in-body simulations. I can't model dark matter baryon scattering, right? So we have modified Gizmo to do this, to include interactions throughout the simulations and consider them self-consistently. I don't have yet results to show you that I'm confident are true, but we are seeing some interesting things. This is just the initial condition, different initial condition. Yeah.
Thanks.
So do you have any other questions? Okay, so in that case, let's thank Vera again.